Good morning, everybody. Oh, the class is shrinking really badly. Thank you, Rochelle, Dal. Thank you, Corey. Yeah, I have about 33 students, but only apparently about 10 are attending. I'm not quite sure if all of those 10 also paying attention to the lecture. Hopefully they would. All right. So, um, I'm talking about these days uh, about mapping, which means when you apply a, uh sort of a function on a region of xy plane or z or complex plane, what happens? What what is the image of that region? So last time I talked about this linear function and z squared, all right? Also, I talked about the function 1 over z, the reciprocal function, which is a combination of inversion to unit circle and conjugation, okay? We did have a bunch of examples, and I hope uh, you practiced on it, or at least learned the topic or looked at your notes. Now, today, I want to talk about um, a concept in mapping, which is called conformal mapping. The question is, what is a conformal mapping, right? Now, in order to talk about conformal mapping, first we need to talk about two curves. When the two curves intersect, at the point of intersection, we have an angle, right? The angle between two curves, here is curve number one, let's call it C1, and this is its parameterization. Here is curve number two, and with its parameterization. So at certain point, they intersect, so the parameter value will produce the same complex point or complex number. So let's say those two curves intersect at this point z naught, right? So here is point z naught. On curve C1 and curve C2, okay? Now, if you graph the tangent line to C1 and tangent line to C2, the angle between these two straight lines is called the angle between those two curves. Well, we have some facts, of course. Um, we know that z prime will give us the direction of this uh, tangent, and derivative z prime 2 will give us direction of this tangent. Let's say um, as when you took derivative, you got these. So uh, for T2, the direction T2 has argument theta 2, and direction T1 has argument theta 1 if you write it in polar format, okay? So what will be the angle between these two? It will be theta 2 minus theta 1, okay? Theta 2 minus theta 1 will be the angle. So with this sort of observation, geometric observation, one can say, oh, look, here is the angle between these two curves. The argument of z prime 2, this is derivative of z2, minus the argument of derivative of the z prime. Now, we don't know which one comes first, which one second, right? But certainly the difference between these two will be either here or here, okay? We are talking about this angle, which is less than 180 degrees. I'm not going to consider this angle, no, just this angle. Okay, with that in mind, now having these two curves in the mapping section or chapter that we are working on, you go ahead and apply a function to this situation, right? So then you have this curve C1, then you have this curve C1, and you apply the function f of z. In UV plane, you are going to get another curve. I call this C prime 1. And that curve Z2, all right, here, the picture-wise. So let's say here is curve C1, here is curve C2. Now you apply the function, and image of this curve is going to be another curve in UV plane. An image of this curve is going to be another curve in UV plane. The question is, after applying the function f, does that function preserve this angle? All right. Is this angle going to be the same as this angle between these two tangents, between two curves? All right. Well, that is what I would like to make it very clear. It is not necessarily the same angle, for sure. Or if this is going in this direction, is, let's say it's 45 degrees. This might go the other direction, negative 45 degrees. So a function, okay, a function that preserves the angle and preserve the sense of the angle or direction of the angle is called a conformal map, all right? So what is a conformal mapping? Here we go. So the definition of sort of conformal mapping, we say the function is conformal at that point if whenever you have two curves passing through that point, the image of those curves under this function will have the same angle and the same sense, right? The same angle and the same sense. This is what conformal is. Conformal at a point, but of course, the function can be conformal at a lot of points. And we love those functions that are conformal everywhere, right? Everywhere. So the natural question is, what is the criteria? Do we have a test do we have a measurement that tells us if given a function it is conformal or not? Well, yes, we do have this beautiful theorem, conformal mapping theorem. Beautiful fact. If derivative is not zero, then the function is conformal. Very simple, right? If derivative is not zero, well, derivative being zero, it's a different situation. But as soon as derivative is not zero, the function is conformal. And the argument is pretty straightforward. It's let's say we have these two curves, and we apply the function as a result. If we apply the function, these are the images of those two curves. What is the angle between these two? Well, no. We take derivative, argument of derivative minus argument of derivative of that one. So this is the angle between these two curves. It's argument of derivative of that less minus derivative of that. Okay. Well, but here you use chain rule. Derivative here will be f prime of z2 times z prime of t. Okay, using chain rule. But whenever you have two complex functions multiplied by each other, the argument is sum of the arguments, sum of argument of f prime plus sum of argument of z prime, 2. Same thing here. If you write it in that way, the argument of f prime and this one cancels. So we have the argument of z prime of 2 minus argument of z prime of 1, okay? So what does it mean? It means that the angle between these two curves, the images, is the same as the angle between the original curves. So that is why when the derivative is not zero, it preserves the angle and it preserves actually the sense of angle. Okay. Any comment, any question? What is the sense? All right, good. I'm going to give you an example, Del Dodson, to make sure that we see what the sense of an angle is. Okay, let's see. Good question. Good question. Let me. Okay. Let's look at these two curves. Here is one curve in parametric format. But actually, you know, this is y equal 2x minus x squared, which is a parabola. Here is another one, parametrization. And this is again a parabola. So if you graph these two parabolas, they will intersect, of course. Here we go. At x equal 1, okay, at x equal 1, both of them, you see y also is 1. That means the point of intersection right here is 1, 1, okay? Or in complex format, 1 plus I here 1 plus I. Good. What is the angle between these two curves? Well, for this curve, which I called it C1, here is C1. Derivative will give us the sort of direction of the uh, tangent line. So derivative is right here. And when t is 1, z prime is 1. So it's this one, which is its slope is 1. That means it makes a 45-degree angle with x-axis. The second one, derivative here is right here, okay? And for 1, t equal 1, you have 1 plus I. So here comes the z prime at 1. Z prime at 1 here is 1, and it is e to the 0, which is parallel to x-axis. That's for curve 1. For curve 2, z prime was 1 plus I. If you write it in polar format, here is its argument, which means it's a slope, all right? It makes the angle 45 degree with the x-axis. That's it. So the angle between these two curves at this point is 45 degree. If see argument of z prime 2 minus argument of z prime minus 45 degree. 45 minus 0 is 1. Now let's apply this function, the conjugation. When you apply the conjugation to those two curves, the imaginary part, the sign changes. So those two curves become these two curves. Here is curve C prime 1, and here is C prime 2, based on previous notation I called C prime, the image. Here is C prime 1. Now, the angle between these two, well, if I call it the argument of z2 minus z1, after applying this function, here is z2, here is, z1. So the argument is going to be negative pi over 4. Okay, negative pi over 4. Although this is 45 degree, it preserved the angle, but it didn't preserve the sense of the angle. When you go from, let's say, T2 to T1, it's negative 45 degree, but here, when you go from T2 to T1, it's 45 degree. So the direction sense, see, here you can think about direction of the angle changed. That's what we call sense of the angle, right? And always remember, if here you go from C2 to C1, in the image also you got to go from image of C2 to image of C1. And in this case, image of C2 to C1, and those are, although Both are 45 degree. One is negative, one is positive. So the direction was not preserved. That is what I meant by sense. Okay? Got it, Adele? Okay, I'm glad you asked that question because that was important. A lot of time people uh, just uh, say conformal if preserves the angle. They don't talk about preserving the sense or direction of the angle. Okay, good. Here are some examples. Oh, look at this function z2 that we discussed last time. Its derivative is 2z. So derivative is 0 only at 0. So this function is conformal everywhere except at 0. Right? So remember, the how do we determine whether a function is conformal or not? Derivative. Derivative's got to be non-zero. So the function z squared is conformal everywhere except at 0. Derivative is 0. The function e to the z. Oh, look at this. Its derivative is e to the z, and e to the z can never be 0. So the function e to the z is conformal all the time, everywhere. All right. Okay. So um, after I explained the theory, of course, the theory is there to help us. We prove the theorem to get a fact that can be used. And the fact here was very simple. If you have a function, it will be conformal at points where derivative is not 0. Very simple. Very simple. Good. Here is 1 over z. We discussed 1 over z last time. It's a reciprocal function, which was combination of reflection with respect to unit circle and conjugation. Derivative here is never 0. So the function 1 over z is always conformal. Okay? How about that linear function? Well, if you take derivative is a. So usually a is not 0, right? Otherwise, we have a constant function. If a be 0, we have f of z equal b. The constant function um, is not really that interesting. So a linear function is conformal. It preserves the angle and the sense of the angle, a direction of the angle. Okay, good. Now today, I'm going to talk about uh, another function, which is called Joukowski's airfoil. Joukowski's airfoil. Well, we know z, we know 1 over z, but when you combine them, things will be extremely interesting. And I'll tell you why they call it Joukowski airfoil. Uh, your book, unfortunately, is very uh, brief. So uh, when I looked at your book, it was just half a page on Joukowski. So here is how your book is treating this um, right example, treating as an example, example three, okay, Joukowsky airfoil, and but uh, it is such an important function that I'd like to elaborate on it or write. And they are talking about, this is the next page, that what Joukowsky airfoil does and why they call it airfoil. But as I said, it is so brief that if you look at that example, you can hardly understand what they are saying in that. I'm going to uh, cover this in more detail. So it's good to analyze this function and get some observation. And at the end, put all these observations together and uh, see what we can do. Okay, the first observation is this. Here is the rule of the function, right? If you replace z by 1 over z, so here you get 1 over z and reciprocal of reciprocal. So it's a very interesting that the image of z and 1 over z are the same. All right? So, example, if you plug 5 and 1/5, you will get the same result. You get the same result. All right? This is just to make sure that I am conveying the message and you get it. So, in UV, in complex plane, the point z and 1 over z are two different points. Okay, like this, 5 and 1/5, they're two different points, but they have the same image, which means this function sends 2 points to 1, right? In a way, it maps the whole um, uh, if it sends 2 points to 1, so 1 should be enough, right, to cover the other plane. So that means this function is covering its image is covering complex plane twice. Its image is covering complex plane twice. Okay, good. That's one observation. The other observation is, oh, let's take derivative. Derivative is derivative of this function, 1, and here negative. All right. Remember conformality? A function is conformal at points when derivative is not 0. But here we get 0 whenever z is plus minus 1. So when it comes to the mapping of this function, I'll show you what happens at these 2 points, plus minus 1, okay? Where derivative is 0. As a result, the function is not conformal at these 2 points. Observation number 3. If we write this, if let z be in exponential format or polar format. Now replacing here the RE to the I theta, and here goes to the denominator, okay? And e to the I theta is going to be, um, or maybe I should do this. So it will be R e to the I theta, and e to the I theta, we can use Euler's identity, which is cosine theta plus I sine theta. And 1 over z, it will be 1 over r e to the negative I theta, because this will be in denominator, you take it to the numerator, all right? Again, you can write this as e to the negative I theta will be cosine theta minus I sine theta, right here. Well, if we bring the real part together, imaginary part together, so this is the u part, this is the v part, the real part, imaginary part. And applying the idea that sine squared plus cosine squared is 1, this actually gives us an ellipse, all right? I didn't write the ellipse, but here is how it works. So u divided by this, u squared, r plus 1 over r squared, plus v squared over this. Is one, it's equation of an ellipse, all right? So, but we got to make sure that this denominator won't be 0. So this is, in a way, writing in polar format, and right away you will see that we are going to have a bunch of beautiful conclusions thus from this in a moment. But first, let's look at the observation number 4. Here's observation number 4. What happens to the unit circle? In unit circle, r is 1. The radius is 1. If you replace r1, v will be 0, right? 1 minus 1. We get 1 plus 1, which is 2, cosine theta. So the unit circle, the image of unit circle, is right here. This is the unit circle. V will be 0. U will be 2 cosine theta. Theta goes from 0 to 2 pi. But if theta goes for 0, you get 2. So the image of 1 is right here, 2. And then you go counterclockwise up to this point. Cosine of pi is -1, so it is -2. So the upper portion of this circle, the upper part, goes from 2 to -2. And the lower part does the same thing. This time goes from -2 to 2. All right? This is what I meant by this covers the twice. All right, it covers the UV plane twice. But sorry, you see, at plus minus one, it was not, the function is not conformal. Now, the angle here between this curve and x-axis is 90 degrees, but it doesn't preserve that 90 degree. It goes right here, okay? The angle is 0. Same thing here. So at these 2 points where the function is not conformal, we have this situation. We go along u-axis to the -2 and come back. So this is the image of this unit circle, right? Any comment, any question? Dale Dotson is asking why this V is 0. See, in previous observation, this was the polar format. Unit circle means R is 1. As soon as R is 1, here you get 0. V is 0. R is 1, here you get 2. So U is 2 cosine theta, V is 0, right? Okay, good. Okay. No, I'm glad you are asking question. I'm sure that others might have the same question, but they are shy to ask. Now let's have another observation. Let's call it observation number 5. Again, I'm going to the polar format, okay? What happens to a circle of radius A? Oh, we took care of unit circle, the circle of radius 1. We took care of that. Now let's look at the circle of, in general, radius A. A is not 1. So we will get this. And as a result, I told you earlier, we get this ellipse. Now I can divide by this because we know that A is not 1. I treated the case of A equal 1 or R equal 1 differently. But now that A is not 1, we have an ellipse. All right, so here is the situation. When A is bigger than 1, we will have these -1 plus 1 inside the circle, which is fine. And the image of this under that Joukowsky function will be this ellipse. Okay, this ellipse. And of course, we know image of 1 is 2, image of -1 is -2, are inside. Okay? Observation number 6. The outside of unit circle will be mapped onto the whole thing except that interval -2, 2. Okay? And inside, the same thing. That is what I meant by it will cover UV plane twice. Okay? UV plane twice. Remember, here I am excluding z equal 1. I am excluding the circle. The circle itself, of course, will go to -2, 2, twice. When I exclude that circle, outside of the unit circle goes to the whole complex plane, excluding this interval inside of unit circle does the same thing. Okay? Here is observation number 7. This Joukowsky is a very interesting function, although it's very innocent looking function, right? Z plus 1 over z. But look, when you're analyzing this function, how many beautiful facts and observations we have here. Now, I'm going to consider a circle that passes through -1 and 1. Its center, of course, is going to be on the y-axis. Let's say beta. Here is the center. And here is the radius. 1 plus beta squared, square root. What happens to this circle? Well, we know that the image of 1 is 2. The image of -1 is -2. When you go on the upper portion of the circle counterclockwise, you cover this curve from 2 to -2. The lower part will go back on that curve, right? So the circle, the image covers this curve twice. This curve twice. But again, because it is not conformal at these 2 points, see, doesn't preserve the angle at these 2 points. Instead of the whole circle, we have just a curve. Well, there is, we can say analytically why actually, if you have z here, it's 1 over z, its reciprocal will be in here, okay? Now there's a little proof for that one. The equation of the circle, the center is beta I, and the radius is 1. Here is beta, so the radius is hypotenuse of this square root of 1 plus beta squared. So that is the equation of the circle, which means that if you write z as x plus I, y, here's what we have. It's the equation of that circle in Cartesian format. This is in complex format. Now, reciprocal of z, this is what I am trying to justify. If z is on the circle, 1 over z also satisfies the circle. Here is 1 over z. Multiplying by conjugate of z, you get this one. So this is the real part. This is the imaginary part. I want to show that 1 over z also satisfies this equation. So here is u, here is v. So u squared plus v minus beta squared. If you square this is what you get. Combination of these two, the same denominator. In numerator, you have x squared plus y squared, so you will get this one. Plus beta squared plus 2 beta y But uh, this one and this one will give you this, all right? But 1 plus 2 beta y, uh, if we square this one, it's just a square, x squared plus y squared. So this will give you 1 plus beta squared. All right? So if z satisfies this equation, 1 over z, which is this guy, that also satisfies the equation. So that is why I'm sort of analytically showing you that the upper part and the lower part, they produce the same curve. So upper part once, lower part another. So this is a circle that passes through -1 and 1. Now I will go to observation number 8, where I would like to consider a circle that passes through 1, but not through -1. So let's say, for example, its center is right here, center is here, and passes through 1. The image of this guy is going to be this. And here is the image of -1, all right? This is -2, actually, right here. The image of the circle under Joukowsky is this one. See, um, Joukowsky's function is conformal everywhere except at these 2 points. So it is not conformal at this point, okay? Doesn't preserve the angle, but everywhere else it is preserves the angle. Good. This is why they call it Joukowsky airfoil, because look, this looks like the aeroplane wing, and this this was done long time ago before they uh, the aeroplane was invented. Uh, so uh, and if we apply to Pascal principle to this uh, airfoil, see what happens. Pascal principle, for those of you who have uh, taken physics, you know what it is. If you have a flow of air, right? Let's say the air is going in this way, where the speed of air is large, the pressure on the surface will be less. And for Joukowsky airfoil, as soon as you have air going in this direction, in the lower part, the air is slower as a result based on Bernoulli's principle. The pressure on the surface will be more. On the top, the air goes faster. As a result, the pressure on the top surface will be smaller, less pressure on the top, more pressure in the bottom, and that is uh, the result of lifting the whole thing up, right? So when air blows, in this direction. Based on Bernoulli's principle, the faster air, the less pressure. The slower air, more pressure, and that causes the vis go up. Okay. Any comment about this Bernoulli's principle? I usually demonstrate this Bernoulli's principle for my students. Let me see if I can demonstrate for you as how this Bernoulli's principle works. Okay, so here is, let's look at it as an airfoil, right? I'm going to blow like this. See, when the speed of air is more on the top, the pressure is less. And the speed of air here is smaller, the pressure is higher. As a result, this goes up, all right? This goes up. One more time, look at this. This is Bernoulli's principle, okay? This is Bernoulli's principle. And the concept of this Tchaikovsky's airfoil. Well, some other observation. Here is observation number 9. Okay, let's see. Observation number 9. This shaded area, applying Tchaikovsky, will cover upper half plane. It covered this part completely. Why? Oh, here's why. You start from this point, infinity, right? Which is the images in here. You go in this direction, come to -1. The image of -1 we know is right here, -2. You go along this circle. Here is I, unit circle. Here is I. The image of I is 0 because you have 1 plus 1 over I, right? 1 plus I plus 1 over I. And 1 over I, you multiply top and bottom by I, you get I minus I, which is 0. So the image of this, and this circle, by the way, we already saw that it covers this much. So C covers 0. D covers D prime, and of course infinity here. So if you go in this direction, you're covering the u-axis completely. Now the question is, why upper half plane, not lower half plane? Well, you just go ahead and plug 2I in Tchaikovsky. And if you plug 2I, you will get 2I plus 1 over 2I, okay? And 2I plus 1 over 2I will give you an imaginary number on top. So 2I plus 1 over 2I, you multiply by I again, this will be my 1/2, so it will be 2 minus 1/2 I. So it is, the image of 2I is somewhere here. That is why it's not lower. So this shaded area, if you apply Joukowsky, will be completely, will cover the upper half plane completely, okay? Same thing with this one, just this part, this shaded area right here. That also covers the upper half plane, all right? So I will leave the argument for you. So that was uh, the observation number. There are other beautiful observations, okay? There are other beautiful observation. I'm just going to stop at this point talking about Joukowsky. And next time I will talk about e to the z and some other functions, of course, as a mapping. So what does e to the z do to different regions of complex plane? That's going to be a very interesting topic. So um, right now, I completely covered this section 17.1. Please go ahead and read that section. As I said, your book is pretty brave on those material. That is why I sort of recommended that you go ahead and get another complex variable book and read those mappings. And any other complex variable book will do better on that mapping. All right, any comment, any question? Okay, no question. Good. Well, I hope you enjoyed today's lecture, and I will see you on Thursday. Bye-bye, everybody. Thank you, Brandon. Thank you, Dell. Thank you, Krish. Thank you, Rochelle, Matthew. Thank you. Thank you, everybody. Take care.